Hello everybody, this is Evrim. In this video I will introduce to you an algorithm from reinforcement learning that is called Iterative Policy Evaluation. Iterative Policy Evaluation is a subject under the dynamic programming, an approach from reinforcement learning. I will be trying to demonstrate dynamic programming by policy evaluations first. Then I will introduce the method to improve it by policy and value iterations. But before proceeding further, I would like to present to you some fundamentals of reinforcement learning. Reinforcement learning is one of the three machine learning methods after supervised learning and unsupervised learning. The idea behind reinforcement learning is creating an agent that can figure out things on its own, learning from experience, and finding its own solutions. We can think of this agent as a learner or a decision maker. What we are expecting from this agent is to interact with its environment and learn from it. The thing it interacts with, comprising everything outside the agent, is called environment. Here we can see an agent-environment interface, and it shows us how an agent interacts with the environment in Markov decision process. A Markov decision process provides a mathematical framework for modeling decision-making in situations where outcomes are partially random and partially under the control of a decision maker. So what does this interface tells us? The environment provides a state to the agent. We can think of this state as a given situation at a given time. The agent takes this state as an input and produces an action from its alternatives and sends it back to the environment. Upon this action, the environment feeds the agent with a new state and a reward for the action. This reward is a concept to teach our agent what is good or what is bad in a given situation. One other thing on the figure 3.1 that might catch your eye and be of interest to you is t and t plus 1 time subscripts of the action, reward, and the state factors. The reason for this is the interaction process occurs one after another. Therefore, each state, reward, and action happens at a time step. In reinforcement learning, the purpose or goal of the agent is to collect rewards passing from the environment to the agent. Thus, the agent's goal is to maximize the total amount of reward it collects. This means maximizing not immediate reward, but the cumulative reward in the long run. The use of a reward signal to formalize the idea of a goal is one of the most distinctive features of reinforcement learning. If we denoted reward with R, the sequence of rewards received after time step t is denoted R subscript t plus 1, R subscript t plus 2, R subscript t plus 3, and so forth. Then, what precise aspect of this sequence do we wish to maximize? In general, we seek to maximize the expected return, where the return denoted gt is defined as some specific function of the reward sequence. In the simplest case, the return is the sum of the rewards, where t is the final time step. In a process or a task that has t time steps and ends at the end of this time step is called an episode, and the task is called an episodic task. These episodic tasks always have an end state named terminal state. Another concept to affect the expected return is the discount rate, and that is usually denoted with a gamma sign. I think it simplifies to think of the discount rate as the diminishing importance of a piece of knowledge in time, like the knowledge meant everything yesterday, today it is less important, and tomorrow it will be insignificant. Almost all reinforcement learning algorithms involve estimating value functions or functions of states or of state action pairs that estimate how good it is for the agent to be in a given state or how good it is to perform a given action in a given state. So, value function will be a mathematical equation that will give us the expected return under a given policy. Then what is a policy? A policy is a mapping from states to probabilities of selecting from each possible action and denoted with pi. If the agent is following policy pi at time t, then pi is our probability of the action in given state. The importance of the value function is that we will be using it as an update rule for our approximation. I do not want to make this more complicated, therefore I will not be giving you all the equations and their derivations. However, this is the Bellman equation for state value function for policy pi, and this is the key concept of the iterative policy evaluation. It expresses a relationship between the value of a state and the values of its successor, and you can think of this looking ahead from a state to its possible successor states.